Hello everybody, Namaskar. In the previous two classes, two lectures, I have discussed about the reciprocating compressor and rotary compressors. Those are basically the positive displacement compressor. Now in this lecture, I will discuss the centrifugal compressor. Centrifugal compressor is generally used for the large capacity refrigeration application. So in this slide you can see that the two views, side view and front view of a centrifugal compressor are given in the left side figure and right side figure. So you can see that in this figure we can divide it into the total 4 zone. So in the first zone, that means zone number 1, this is basically the inlet of the compressor, and for this case there is also guide vane. So at the center there is an inlet of the refrigerant, and this is pouring to the guide vane. So we can get some velocity of the refrigerant after this guide vane. And then zone 2, this is basically the consist of the rotary vanes. Okay, so these vanes are basically used to convert the the electrical energy or the mechanical energy to the kinetic energy. So in this zone the refrigerant will gain both the pressure energy and kinetic energy, and after that there is a diffuser portion, that portion 3, zone 3, this is the diffuser portion. So in this diffuser portion the kinetic energy of the refrigerant vapor, that is again converted to the pressure energy, and the zone 4, this is basically the outlet of the refrigerant from this centrifugal compressor. So in case of positive displacement compressor, we have seen that the increase of pressure of the refrigerant, that is basically done by the compression of the refrigerant vapor. Compression means the decrease the volume of the refrigerant vapor. So decrease of volume, that will give the increase of pressure for the refrigerant in case of positive displacement type compressors like the centrifugal compressor and like the rotary compressor and reciprocating compressor. But in the centrifugal compressor, for this case there is no change in volume. So for this case we can assume some control volume. So for this case basically the kinetic energy which is given by the rotary vane of this compressor, that kinetic energy is ultimately converted to the pressure energy. So that means the pressure is increased due to the conversion of kinetic energy to the pressure energy. So for this case basically the electrical energy is first converted to the mechanical energy, and mechanical energy that is converted to the kinetic energy, and then the kinetic energy is converted to the pressure energy. So by this way the pressure of the refrigerant is increased in the centrifugal compressor. So this figure actually shows that how the enthalpies are changing in the centrifugal compressor. So this is the enthalpy entropy diagram. So for this case I is represent basically the inlet condition of the refrigerant. So Hi, this is the inlet enthalpy of the refrigerant, and Ci, this is the inlet velocity of the refrigerant. So that means the total pressure is basically equal to the total enthalpy at the inlet, that is the Hi0. Okay, Hi0 is the total enthalpy, that is the combination of the static enthalpy and the kinetic energy at this point. Then at the inlet vane, that means at the guide vane at the inlet, when the refrigerant is flowing to the guide vane at the inlet. Okay, so I is the inlet condition of the refrigerant. So at the point I, the total enthalpy Hi0, that is the combination of the enthalpy Hi plus the kinetic energy Ci square by 2. Then when the refrigerant is flowing to the inlet guide vane, So the outlet condition of the inlet guide vane, that is the inlet of the rotary vane, so that point is on. So during this condition you will see that the kinetic energy will decrease and your enthalpy will decrease and kinetic energy will increase. Okay, so anyway, that combination of this kinetic energy and enthalpy, that is the total energy at the point on. So the I to on, there is no external energy change. So that means the total enthalpy at point I, that should be equal to the total enthalpy at point on. So that means the HI0, that is equal to the H on 0. Then that is going to the rotary vane. So state point 1 to 2, this is the flow through the rotary vane. So during this process, the kinetic energy, that is the input parameter. So that means the work for the compressor, that is given here in term of the kinetic energy or the rotational energy of the vane. So in this case, the enthalpy and kinetic energy both will increase due to the work transfer inside the compressor. So the outlet condition is point 2. So at the point 2, enthalpy is H2, and for this case we will get very high velocity, that is C2. So that means the C square 2 by 2, that is the kinetic energy gain in between the process 1 to 2. So at the point 2, the total enthalpy, that is equal to the H20, and H20, that is equal to the H2 plus the kinetic energy at this point. Then after that, the 2 to 3, this is the process inside the diffuser of the compressor. So during this process, the kinetic energy is converted to the enthalpy or the thermal energy. So that means during this process, the kinetic energy will decrease and the enthalpy will increase. So but the total enthalpy, that also remain constant as the point 2. So that means the at point 2 and 3, the total energy are remain same. So that means the H20, that is again equal to the H30. So at the point 3, enthalpy is H3 and velocity is C3. So that means the H3 plus C3 is square by 2, that is the total enthalpy at point 3, that is H30. Then the point 3 to 4, this is the process which is occurs at the outlet or volute casing of the centrifugal compressor. So in this time, in this process also, there is a decrease of the velocity of the refrigerant, and some of the kinetic energy will again converted to the pressure energy or enthalpy. So that's why the enthalpy at point 4, that is higher than the enthalpy of the point 3, and at the point 4 the velocity is C4. So that means the total enthalpy at point 4, that is H40 plus the C4 square by 2. So that means the total process, we can consider the I to on, this is the process at the guide vane of the compressor. Then on to 2, this is the process through the rotary vane of the compressor, and then 2 to 3, this process occurs to the diffuser section of the compressor. Then 3 to 4, this process is occurring through the outlet vane or volute casing of the compressor. So the I is the inlet condition of the refrigerant and 4 is the outlet condition of the refrigerant in a centrifugal compressor. So the energy balance for the different section of this centrifugal compressor we can write by this way. So initially there is a involute casing, that means there is a guide vane in this case. So for this case, so guide vane means the fixed vane. So for this case, the total enthalpy at the inlet Hi0 can be written as Hi plus Ci square by 2. So that also equal to the H on plus C on square by 2, and that is equal to H on 0. So total enthalpy at point I and total enthalpy at point on both are same. Okay, so then in case of impeller or the rotary vane section, so for this case we are giving the energy in term of the rotation of the impeller. So rotational energy of the impeller. So that means the work is a input for this case. So this work energy is converted to the thermal energy or the kinetic energy. So that's why this work energy, that is equal to the enthalpy change H2 minus H1 plus also the kinetic energy change H2 square by 2 H2 square by 2 minus H1 square by 2. So H2 minus H1, this is the change of enthalpy, and the second term, that is represent the change of kinetic energy. So that means the H2, so that means the total enthalpy at point 2 minus the total enthalpy at point 1, this is the total work input to this compressor. So this also can be written by this way, that H20, that is equal to H2 plus C2 square by 2, that is equal to W plus H1 plus C1 square by 2, and that is also equal to W plus C10. So after that there is a diffuser. In the diffuser section there is no external energy change or energy input or output. So for this case the total energy will be remain same. So that means the H20, that is equal to H30, whereas the H20 can be written as the enthalpy plus kinetic energy at point 2. Similarly, that is equal to the enthalpy and kinetic energy at point 3. Then after that there is a outlet section, that means the velvet casing. So for this case also the total energy that will be remain same. So that means the H30, that is equal to H40, that means the H30, that is equal to H enthalpy and kinetic energy at point 3, and also that is equal to the enthalpy and kinetic energy at point 4. So that means for this case the that total enthalpy change, that is basically equal to the total work input to this compressor, or we can say that the work input to the compressor, that is equal to the total enthalpy change H20 minus H10, because the outlet condition is H40. So H40 minus Hi0, that also can be written as H20 minus H10, and that is equal to the enthalpy change in between the inlet to outlet. So H4 minus Hi plus the kinetic energy change in between the inlet and outlet, C4 square by 2 minus Ci square by 2. So for special case, if we assume that the inlet velocity is nearly equal to the outlet velocity of the system, and that if you neglect that, or you can neglect this the inlet velocity and outlet velocity, so that means the work transfer, that is equal to the enthalpy change in between the outlet at inlet. So for the cycle analysis, in case of the vapor compression cycle, we have already assumed that the inlet kinetic energy and outlet kinetic energy, or kinetic energy change inside the compressor, that we have neglected. So that's why we have already written the work input to the compressor, that is equal to the enthalpy change during the process. Okay, so that means the only W we can retain as a H4 minus Hi. Okay, so for this case, in case of centrifugal compressor, how we can change the capacity or mass flow rate of the refrigerant? So there may be the various methods how we can control the capacity or mass flow rate. So there are 4 methods which are listed in this slide. So one first method is the adjusting the pre-rotation blades of the impeller inlet. So that inlet, at the inlet casing, the blade at the inlet casing, that we can adjust to adjust the opening, okay, opening for the refrigerant inlet. So by adjusting that pre-rotational blades or fixed vane, if you adjust the fixed vane, then we can control the inlet flow rate to this compressor. So that means ultimately we can control the mass flow rate of the refrigerant through this compressor. Second one is the speed variation. So we know that the total flow, that is basically depending on the speed of the rotor or the speed of the the rotational vane, okay, or impeller. So impeller speed, higher speed will give the higher flow rate and lower speed will give the lower flow rate. So by the control of speed we can adjust the flow rate of the refrigerant to this compressor. And third option is that we can, if we maintain the condenser pressure or outside pressure, then total mass flow rate to this compressor, that is also depending on what is the pressure difference in between the inlet and outlet. So the decrease of outlet pressure, that will decrease the flow rate of the refrigerant, and increase of outlet pressure, that will increase the flow rate of the refrigerant. So that by adjusting the condenser pressure, we can also control the flow rate of the refrigerant inside the compressor. And another is the hot gas bypass. So if you bypass some flow from the bypassing from the flow inside the compressor. So if you bypass some flow for the compressor, so that also can be used to control the mass flow rate, total mass flow rate to the compressor. So that the first option and second options are generally used to control the mass flow rate to the compressor. Okay, so now if you see the variation in between the pressure ratio and the flow rate, so that the pressure ratio and flow rate, that is depending on each other. So what I have discussed earlier case, that we can change the pressure ratio. So changing in pressure ratio can change the flow rate, or the flow rate, change of flow rate also can change the pressure ratio. So both are interdependent. So if you see the behavior in between the pressure ratio and volume flow rate, so this type of behavior we will see. So that means for if you change the flow rate, then you will see that at the certain flow rate we will get the maximum pressure ratio. So basically this is basically that balancing in between the flow to the rotary vane and the flow to the diffuser. Okay, so if you adjust the flow rate to the diffuser and flow to the guide vane, so that will give basically the maximum flow rate. So sometime if I see that if the flow rate to the rotary vane, that is higher, and the flow to the diffuser, that is lower, so basically the higher and lower case, that will create some instability in the system. So that's why we can get some surge line, so where basically the instability or mismatch in between the impeller flow and the diffuser flow. Okay, so we will always consider the right side of this figure. So that means which will basically give because our main purpose to use this type of compressor is to get the higher flow rate. So we will always use the condition which is related to the higher flow rate region. So that means for design point 1 we can use for this compressor. Okay, so there are various advantages by using the centrifugal compressor. What I have already told, that this is basically used for the large capacity applications. So for the large capacity applications, there is no other alternative to the centrifugal compressor. So for the industrial application of the refrigeration system, generally centrifugal compressor is preferred, or if you consider some case, even for the house the building applications where let's say for example we are using the central air conditioning system. So this type of cases where the flow rate needed is very high, so for that case the centrifugal compressor is generally preferred. Okay, so for any type of central air conditioning system, the centrifugal compressor is used, and for any industrial application and industrial refrigeration system, centrifugal compressor is only used for that case. Then the second advantage is that this has a very high efficiency wide range or load range. With the speed control, speed also you can control very easily for this compressor. So this compressor has a good control system, and also you will get the higher efficiency for this case. And for this case, flow rate is very high per unit size of the compressor, and then this also has the capability to achieve the smooth reduction of flow rate, thereby the reduction in the cooling capacity. So for any case, if you want to change the if the cooling load is changing, so for that case we have to change the mass flow rate. So for this case, the change of mass flow rate, that process is very smooth as compared to the other type of compressor, and this has a very flat head or the pressure ratio and the capacity characteristics as compared to the reciprocating compressor. So at last, if I go for that for various applications when we are using the vapor compression system, then what type of compressor can be used for the different type of cases or different type of application. So in general, the best of the refrigeration capacity we can choose the various type of compressor. So I have already discussed that for the small scale system where the compressor capacity or cooling load capacity that is very low, so cooling load capacity up to 8 kilowatt. So for this type of applications, we will always prefer the rotary type compressors. For example, the household refrigerator, that commercial freezer and household air conditioning system. So for all these cases, we will always prefer the rotary type compressor. Then when we will go for the certain slightly higher capacity as compared to this, like that capacity, let's say from 80 kilowatt to the 350 kilowatt or the 100 ton of refrigeration capacity. So within this range, reciprocating compressor is normally used. And another advantage of reciprocating compressor is that for the reciprocating compressor, the pressure ratio that we can achieve, that is much more as compared to the pressure ratio or pressure rise in case of rotary compressor. So some refrigerant, if you have to maintain the very high pressure in the condenser, so for that case the reciprocating compressor is most preferable, like in case of ammonia system. In case of ammonia system, that condenser pressure is approximately 40 bar. Okay, so and for this case we need a high pressure rise. So for the ammonia system, the rotary compressor is generally not used. For this case, reciprocating compressor is best suited for this application. Similarly, if we consider the CO2 system, so for the CO2 system, the pressure difference in between the evaporator and gas cooler, that pressure difference is very high. Let's say for example, for the evaporator pressure we have to maintain let's say approximately 40 bar, and in the gas cooler pressure may be about 100 bar. So for this type of pressure difference or for this type of pressure rise, the rotary compressor is not suitable. So for this case, the reciprocating compressor is useful for this condition. Okay. Then again, if we go for the higher size or high capacity, so for that case centrifugal compressor is used. So centrifugal compressors are usually suitable for the system of 500 kilowatt or higher cooling capacity. That means for the central air conditioning system, for the industrial application of the refrigeration system, for those applications the centrifugal compressor is generally preferred, or centrifugal compressor is used for those applications. And in between these, that means the 300 to 500. So that means the in between the reciprocating compressor to the centrifugal compressor, in between applications, the screw compressor can be used within that range. Okay. So that means the up to 100 kilowatt rotary compressor, then up to 80 kilowatt rotary compressor, then 80 to about 350, that for the reciprocating compressor, and then again for the higher capacities 350 to 500 For that case, screw compressors are used, and again above that, that is for that case, that means for the high capacity, centrifugal compressors are used. And the scroll compressor, this is basically the newly developed compressor as compared to the other compressors. So that's why the scroll compressor has been developed for the variety range or wide range of the cooling capacity. So in general, for the medium range, the scroll compressor compressors are widely used, like the commercial APIs and applications. The scroll compressor is most suitable compressor for that APIs and application. And some other comparison also already, which I have discussed in the previous slide, so which can also summarize, or there may be some other difference in between the different type compressors. So that I have, there are many differences, so but some important differences in between the different compressor that I have listed in this slide. So the first point is the screw compressors are more efficient at the full load, whereas reciprocating compressor has the better efficiency at part load. And second point, the reciprocating compressor have the longer operating life as compared to the screw compressor, and screw compressor has the lower noise level than the others. Okay, so scroll compressor, that is the newly developed compressor, and that has been developed for the various applications, although this is mostly used for the medium capacity applications. Thank you.